system of equations in two variables. I think this is something most of you have seen before in previous algebra classes. So a system of equations is when we have more than one variable and we're looking more than one variable and more than one equation, and our solution needs to satisfy all of the equations in the systems. If we substitute the values x and y into both the equations, it makes both the equations true. The solving methods, there's three different solving methods. The graphical solving method, we can solve both equations for y to make them easy to graph, and then when we graph them, the graph represents all the solutions to a particular equation, and the one solution they have in common is where the two lines intersect, and that's the point 0,2, which is our solution. Another solving method, special cases first. That one had one unique solution. Some systems have no solutions. In the case where you have two parallel lines, they never intersect. There's no point in common. So we say there's no solution to the system, or we can say the system is inconsistent. And then others are dependent, which means they have an infinite number of points in common, which basically means they're at the same line. So when you graph them, they're on top of each other. So there's an infinite number of points that satisfy both equations, an infinite number of solutions. And this is where we'll differ a little bit from what we did in Math 95, for those of you who took Math 95. Not just any point is a solution to the system, only the points that lie along this line. So what we want to do is describe the points that lie along this line. So one way to do it is to say y equals some arbitrary constant, and then describe x in terms of that constant, or we could say let x be an arbitrary constant and describe y in terms of that constant. The idea is to have something so that we could easily then find pairs of values that are solutions to the equation. So the C notation bugs a lot of students. If you just want to say the solution is x and then describe y in terms of x, that's okay. It means exactly the same thing as describing it in terms of C. And then if we've got a series of values, we could pick x, an arbitrary x, calculate the y in terms of that value of x. Let x be 0, then y is 3. Let x be 5, y is negative 7. And so this could be our solution set. The book's going to write it this way. If you use this notation, that's fine with me. Okay, that was the graphing method. Another method is the substitution method. That's where we solve one of the equations for one of the variables and substitute it into the second equation. So for this particular system, we decided to solve the second equation for y. And the reason we chose that particular variable to solve for is because it has an understood coefficient of 1, which means we're not going to get into a bunch of fractions when we solve for the variable. So brought the y over, brought the 13 over, y equals 2x plus 13. And then I'm going to substitute that expression for y into the first equation, replacing the y with the 2x plus 13. That gives me one equation with only one type of variable. I can solve for x, but now I'm not done yet. I still need to go back and find y. So going to either of these two equations, I can substitute my now known value for x and solve to get the y. And then my solution is actually composed of two different numbers, a value for x and the value for y. And then, doing the check. When you do the check, be sure to check in both the equations, and then you know for sure that you've got a solution to the system. Then there's the elimination method, which is probably less intuitive, but probably more efficient in more situations. And what we're going to do is take negative 2 times equation 1. And that way our coefficients for the x will be a negative 6 and a positive 6. And so they'll wipe each other out when we add the two equations together. So that's the way the elimination method works. We want to eliminate one or the other variable. And to do that, we multiply one or both of the equation by carefully selected constants in order to get both coefficients the same, only one positive, one negative, so that when we add the two equations together, we eliminate one of the variables. So again, multiplying the first equation by negative 2 gives us a new equation. We didn't change the second equation. When we add them together, the x's are now gone. We can solve for y, and then we can substitute that value for y back into either of the two original equations and solve for the x to get our solution. This particular solution, if you think about it, you can see why the graphing method is so limited. trying to read these particular coordinates off of a graph would have been very difficult. So that's why we want algebraic methods also for solving equations. Now, when you're solving algebraically to identify the special cases, what you're going to see is either one of two situations. This particular system, we are multiplying the first equation by -2. Again, that's pure coincidence, by the way. We don't always multiply the first equation by -2. But what we've got now are a -2x and a positive 10x. And so those do eliminate each other. But coincidentally, the y's are also being eliminated. And we're left with 0 equals 7, which is not true. This is false. So this is a no solution situation. And then this system here looks like it'd be most easily solved by substitution, since we've already got a y isolated. So using substitution, solving for y, what we're left with is 6 equals 6, which is true. It's not very interesting, but it's true. And so this is going to be the infinite number of solutions. We don't know anything about x or y, but we do know that these systems are actually identical to each other, these two equations. And so this will be the infinite number of solutions case. And so to describe the solution set, we can say let x be an arbitrary constant c, and then the y coordinate would be essentially -2c plus 3, -2x plus 3. Looking at word problems, don't get intimidated. There's really only 2 or 3 different types of word problems and just different variations on them. This would be one of the how much of one plus how much of another equals the total amount type of story problems. So we're going to go shopping at our local nursery. I'm going to buy 6 petunias and 4 marigolds, and I spent $13.50. My neighbor bought 4 petunias and 8 marigolds and spent $13. So as we're out there planting our flowers, we get to discussing the situation and wondering how much did the individual flowers cost. So I bought 6 petunias plus 4 marigolds and spent $13.50. My neighbor bought 4 petunias and 8 marigolds and spent a total of $13. And I'm yet again multiplying the first equation by -2. Again, that is not always what we need to do. But by doing that, I eliminate the marigolds from the equation. I can solve for the petunias and then go back and find the cost of the marigolds. And then this is a mixture type problem. So say I've got ice cream that's 50% fat and more ice cream that's 20% fat, and how much of each to produce 20 pounds that is 30% fat. So if x and y are the unknown amounts of each of the individual ice creams, and I know I want to get a total of 20 pounds of ice cream, I can set up my equations. Here's my fat equation. Here's my total volume of ice cream equation. And this one solved easily with the substitution method, and solving it out and getting my solution.